Ladies and gentlemen, I would like to welcome you to this session, the fourth plenary session. I would like to ask you to take your seats, and then I would like to start with the introduction of our speaker of this afternoon, Julie Brigham Grette. Me personally, I'm a paleontologist working with mammal fossils, not only with large mammals like mammoths and rhinos, but also with these very tiny mice, these small creatures which you can find everywhere. And also you find a lot of fossils in the fossil record, in the boreholes. And at some moment I found fossils, molars from a vole, I didn't know what it was, at a depth of about 64 meters in a borehole in the Netherlands, and in deposits which were around 2 million years old. And it was, I didn't know what it was, and I showed it to colleagues in the Netherlands, no idea. I showed it to colleagues in Russia, no idea. And at some point I was in America at a meeting and I showed it there and they say, hey, this is interesting, where do you get it from? I said, from the Netherlands. He said, it's impossible, because it's an endemic American species. I said, no, I found it there, I'm sure. So we invited the people from America to come over and to look at the material, to look at also the rest of the fossils, and they even found a few more molars, which was very, very, very interesting. But then we had to, how is it possible that an endemic species, which is only found so far in the US, also occurs at the other side of the world in the Netherlands in a borehole at 64 meters. And then we started about speculation how to do it, and we looked at the rest of the fauna, and it was clear that it was a cold fauna migrated from the north to the south. And then also we said, yeah, the only option is that there must be a bridge between America and Eurasia, so the Beringian Bridge must be the way the species passed during a very short period of time. And then of course you get interested in Beringia, and then you go into the literature, and very soon, of course, you come across papers you wrote about climate change in Beringia, the opening of the Bering Strait, but also the closure. And so that's also why I was very interested and very excited when your name was mentioned, when as an option for a plenary speaker. I said, yes, great, because I'm really interested in Beringia because of this find, and not only because of that. So therefore, I'm really very, very happy, because if you need one person who can say something about Beringia, about the climate change there, it's Julie Brigham Grette. Julie is an expert in Arctic climate change, recorded in the ocean and terrestrial sediments of Beringia. She's especially knowledgeable about the climate change of the last few million years. She was chair of the Polar Research Board of the US National Academy of Sciences, past president of the American Geophysical Union, past president of Quaternary Division of the Geological Society of America, and she's elected fellow of the American Geophysical Union and of the Geological Society of America. May I give the floor to Julie Brigham Grette.
Thank you, Mr. President, and thank you to the AMCA organizers for inviting me to give this talk. This is a great introduction, thank you very much, because I'm going to show you that what we know about the Bering Strait is really a mess. And so I'm going to talk to you about some of the things that I've been thinking about over the last 5 to 10 years, and how we need to reorient our approach to understanding the role of the Bering Strait in climate change. So I'm going to start with this. This is my favorite Chinese proverb. If we don't change the direction we're headed, we're going to end up where we're going. So yeah, time for change, the name of the conference here. And so I also like this website. If you haven't found the Climate Action Tracker, it shows you very clearly that we don't have much headspace before we get to the 1.5 degrees in the IPCC agreement. And unfortunately, present-day policies put us up here projecting somewhere by the 2100, getting into temperatures that are in the range of about 2 to 3 degrees. And even the best-case scenarios aren't really very optimistic. So we really have a lot to do about that. And just to place how quickly this is happening, we all know this. We try to communicate it. I know a lot of you do. But Greta Thunberg will be 97 in the year 2100. So within the lifetime of one person, we're seeing these massive changes. So let's think about that context. This is a figure modified from Burke et al. The lower part just gives you snapshots of today, the last deglaciation, the last few interglacials. Here's the Pliocene, and then back into the Paleocene. And on top now is plotted the PCO2 for those intervals. And of course, that red line shows you where we're at about 420 ppm. That's where we're at today. So what are the consequences of that? And I want to also introduce you, if you haven't found this website, I really encourage you to take a look at it. This was put together from a research collaboration network where the community came together to compile all of the PCO2 estimates for the past, and it goes back to 70 million years ago. You can click on the proxies on the left, and you can get rid of them or add them back and forth. You can also draw a box around what interval you're interested in. Here's the last 4 million years. And also on the right-hand side over here for for reference is the Epica ice core CO2 record. And so we can zoom right into, here I've just selected the boron to make it simple. We select into the 3 million years ago. And if we can go in and blow that up. This is what that estimate looks like. And of course, this is where we are today. In another 10 or 11 years, we'll be past 450 ppm. We're going to start to leave the Pliocene atmosphere in no time. So what was the world like? And I'd like to introduce this concept, which I've learned from working with indigenous people in Alaska. The idea of remembering forward, using our past. Inuit people think about the past 7 generations and the future next 7 generations. So this idea, I thought, works really well with the paleoclimate community. Remembering forward, we're going to remember what's happened before to think forward in the future. So what was the world like back in that time? Well, let's talk about sea level. And we don't have to go very far from Italy to Majorca to see one of the most amazing, peculiarly interesting speleothems that record sea level in the Pliocene. And as you can see here from this amazing record that was published a few years ago, Pliocene sea level with about a 2 to 3 degree warming was in the range of 16 to 17 meters, and some of the warmest parts of the Pliocene may have been as high as 23 meters above present. So that has got a lot of people's attention. And it's not the only place. We can go to other parts of the world and find these really high sea level evidence. Of course, we have to accommodate for GIA, the dynamic topography, and so on, to reconcile these. This is a record from New Zealand, where again they've got from 3.3 to 2.6. You can at least see the amplitude of sea level within the Wanganui Basin here. And again, the average sea level they think maybe in this by the way is amplitude, not sea level height in this figure. But again, sea level in the range of at least 12 meters or so. So what I like to do when I'm talking to policymakers, which I get a chance to do once in a while, I try to put this figure up when I'm trying to explain sea level, that in fact, every degree matters. And so if we look at a 1 degree change, we have consequences, a couple of meters of sea level. If we go to 1.5 degrees, like the last interglacial perhaps, we're looking at 6 to 9 meters, depending on where you are. And the Pliocene maybe somewhere around 20 meters, and even worse if we go even warmer. So again, remembering forward, every degree matters. So let's again look back at the Pliocene. So this is my perspective of the Pliocene. This is one of Blakely's maps that he's reproduced. And the only thing missing here is he didn't have the ice sheets. There's high mountain glaciers here in Alaska and also on the east coast of Greenland that were clearly putting out IRD, ice-rafted debris, even 8 million years ago. 7 million years in Alaska when the mountains rose up through the snow line in order to produce these glaciers. But certainly, the Bering Strait was open. This opened around 5 million years ago. And we also had no breakup of the Canadian Arctic Islands at this time. So it was a much more continental environment, and we have, as I'll show you, evidence of forested conditions right up to the Arctic Ocean during this time when CO2 may have been around 400 ppm, and the world was about 3 degrees warmer than today. I wanted to stick this in. This is for Alan Ashworth. Yes, the beetles matter. So this is some work from Elias and Matthews, looking at a number of sites. Let's see, the next click. Here are the sites, number of different individual sites where we find stratigraphic evidence of a warmer world. So this is just a relative temperature difference from, this is around 6 million at this end, 0 here at the top, and again, various sets of deposits, which I'll just highlight a couple of these. So we knew from just even beetle evidence years ago that in fact these sites were so much warmer than today. So we're going to go, first of all, to a place called the Beaver Pond site at the next one here. And if we go to the Beaver Pond site, this is a site on Ellesmere Island where many people have worked over the years. And Fletcher et al. Particularly put together a nice paper in Climate of the Past. If you haven't seen this, they go through, in addition to using biomarkers and a lot of other kinds of more modern techniques, really classify what this area was like. It had vegetation, much like maybe Washington State, parts of the Yukon and Alaska. That's kind of what this area was like at that time. And yes, fossil camels are up there as well at this time, at closer to 3.9 million based on the new age estimates in this particular paper. Okay, now just to the left of that, to the west of that is another site called Meehan Island, and I'm showing you the jacket cover from the GSA. I just love this picture because you see all of the big chunks of wood. This site is been studied for a long time by a number of people. In fact, several of the co-authors on this paper are not with us anymore. So this has been a long time in the making. This site, which is really interesting, starts with forested conditions here, a high sea level event, open or forest tundra here, then on top of that is another marine high sea level event, and then open tundra to forest. So open. So this is thought to be the first evidence of tundra in this part of Canada. And based on all of the age information we had putting together this paper, we came up with 2 age models. The marine units contain very warm, loving mollusks. So they're not supposed to be in the Arctic Ocean. They're very, very warm. And we place them either at around 2.9 to 3.2 million years. This is my personal favorite, but I think John Goss has some new cosmogenic ice beryllium ages that kind of favor the second model, putting the older marine unit down here at around 4.3 and this one about 3.5. Nevertheless, a really interesting site, and the important part about this is the top of this site is the last time that we had a contiguous landmass, and after this, the islands of the Canadian Arctic were formed by the first major glaciations that happened at that time. So this is kind of what it looked like at that time. So now let's go to Alaska, to another site, and this is, so we'll run over to northern Alaska here, and This is where we found a lot of these fossil voles and things like that in these deposits. Right there is the Gubic Formation, which this is where I cut my teeth on the early work in the Arctic almost 40 years ago now, where at that time I found a series of shorelines across the north slope of Alaska, and the highest ones, they're up here at 40 meters. They're not compensated for the GIA effect, of course, but in these deposits that date from 2.6 to 3.0 million years or so, we found extraliminal mollusks, again, with water temperatures 9 degrees above present. One of these deposits has sea otter bones in it. Sea otters don't like sea ice. So again, we published a paper saying the Pliocene had to have been ice-free. We said that in 1992, and of course now we're learning more and more about the ice cover in the Arctic. So moving to another site, this paper was just recently published, but boy, the Cape Copenhagen Formation, I worked on it as a graduate student 40 years ago doing the amino acid geochronology on the bivalves that Sven Funder gave me from this site. And so this new paper, again, a lot of the sites I've been mentioning are all in this little figure in this paper as well. And it shows a till with a glacial marine unit and then interglacial deposits on top of that. And as Ingrid mentioned yesterday, it now has this really impressive DNA data that show what that world was like. And so for thinking, when I show this to policymakers, I hear a gasp in the room because they can't believe that Greenland looked like this at any time in the past. So this really gets their attention. So this is really influential to help us think about, yeah, Greenland really was green. It was, you know, it was kind of sold as being green, but it really was green. And I'm afraid Greenland wants to be green again here in the future. So anyway, I just showed you a bunch of different sites where we have information about a warm Pliocene, but where could we find it all in one place? And I was just so lucky to be part of a group working with Russian colleagues who pointed us to Lake Elgagikin, which is a meteorite crater lake located right here between glaciated high mountains, but this basin was never glaciated in the past, and we were able to get a 3.6 million year continuous record out of this site. Here you can see the rim of the crater and its age at just slightly younger than 3.6 million. Then later, the lake is 175 meters deep and 18 kilometers in diameter for the bolide. This was an international project, and I do want to say there were Germans, Russians, Americans, and Austrians. And we had two objectives for this project. One was to really do great science. We were so excited about this site. It took us 15 years to get the money to do it. But we also wanted to be friends afterward with the publications, and we've been successful with that. So this is just the recovery and our picture when we finally hit the injected impact site. So the Elgagikin record produces this opportunity to look well beyond the Antarctic ice cores into all the way back to 3.6 million. And I also want to point out that in the subsequent slides here, I'm going to make a point about the 100K world. A lot of you have heard about the changes in glacial interglacial changes on 100K time scales versus what we often call the 41K world. So I'm going to differentiate between those two. So one of the major breakthroughs from the Elgagikin record, in my opinion, is really been, one of the things has been looking at how we went from a forested Arctic with walnut and larch, hemlock, fir, pine, in the early part of this record to one of tundra. And to me, this is really amazing. Can you imagine doing sedimentary DNA on this stretch of material? So we're gathering those samples right now to send them off to Denmark. And let me go to this one. And this also is published by Pavel Tarasov using a biome model came up with this, which I think is really fascinating, a trend in forest versus open tundra landscape, and you can see how that was extremely complicated. It wasn't like somebody shut off the lights and it got cold and there was tundra. It's much more complicated. So we have a lot to learn from how this transition goes from 3.6 million to 2.2, at least in this record. And I think this was a phenomenal piece of work by my colleagues. We also were able to show that in the Pliocene, if you run a cold orbit on the left and a warm orbit on the right, doing climate modeling, this is from Rob DeCanto and his students, and if you see here, the first panel is 200 ppm, 300 ppm, 400 ppm. What we found was that the only way you could keep the forested conditions, like we see in the record, at the lake, you had to have PCO2 at least in the range of 400 ppm. So that made sense, and it kind of confirmed what all of these other proxies were saying. And again, this was published quite a while ago, and now we have real proxy data to back that up. The other thing we did was we identified, in my mind again, really important thing was we identified super interglacials, and we identified them based on sedimentology. If you look at this right here, this particular sediment facies here represents this kind of environment when every time you see it, the forest came back to around the lake. This is a glacial, what we call glacial phase. This is when the lake froze over solid, just like the lakes in Antarctica. They don't open up in the wintertime. And that isn't seen until 2.6 million. So we don't have that lake freezing over permanently until 2.6 million years ago. And then these are the kind of normal interglacials. And these are all the sediments of the Pliocene look like this. And these, in fact, parts of these sections, I think, are varved. So this diagram here, just a little complicated, but here's the 41K world, 100K world. These little numbers up here are the isotopics super interglacials. And down here at the bottom is the A, B, and C coding of the facies. So the red squares here are the super interglacials. And the only point I want to make with this slide is that there's 17 super interglacials in a 41K world and only 2 in the 100K world. So this says something about the dynamics of the 41K world that's really, really different to us. And I also want you to notice that stage 5E is not a super interglacial by our definition. Many of these super interglacials are associated with high sea level. Sea level isn't preserved everywhere, always, but we know that many of these are associated with high sea levels. And so if we have high sea level, what melted? And again, a little over 12 years ago, the Andril project came out with this coring below the Ross Ice Shelf. I'm sure many of you have heard about this. They brought up this core from underneath the ice shelf and looked at the periods of time when the Ross Ice Shelf didn't exist. And you can see here, let me explain this figure. We're going from 2.2 to 3.6 million. This next green curve is the mean temperature of the warmest month at Lake Elgagitkin. You can see the dotted line is today, the Holocene average temperature. So summer temperatures were largely well above today. In fact, instead of 8 degrees, sometimes as high as 15 degrees C in the past. You see the evidence of an M2 event here. And now in Antarctica, under the Ross Ice Shelf, the yellow areas indicate areas when the Ross Ice Shelf disappeared. And I heard a talk this morning where they're modeling that and, of course, getting rid of the West Antarctic ice sheet in the session today after 11 o'clock. And so we think we can match some of these periods of time when the West Antarctic ice sheet disappeared, and we had these super interglacials early on in the early Pleistocene that seemed to match. And so we're still working on how those match up and why they should even match up at all. So that's kind of maybe a story for another day that I can talk about. Let's see. So now let's take a look. So we've set the stage. We see all these super interglacials. Now let's take a look at the MPT. So that blue box shows you the timing of the MPT. And in the middle of that period is stage 31, a very, very strong, warm interglacial. It was warm in Antarctica. The West Antarctic ice sheet disappeared, and we know now that it was very warm. In fact, it was warm for almost 50,000 years around the time of stage 31 at that time. So we've just published a paper in Climate of the Past. This is actually from one of our senior undergraduate students. He was amazing, Kurt Lindberg, who did biomarker work with Isla Castaneda, working here. This is the temperature record from this, and here in bright red is the stage 31. But what's interesting is the biomarkers seem to suggest that both 21 and 25 were also very warm, impressive, like the stage 31, and yet they fell outside of our initial idea of a super interglacial. So we're starting to learn more about what some of these other parts of the record are, and Isla Castaneda is working on a big paper on all of the entire record that will be forthcoming. Okay, so what else about the MPT? So some years ago, Leonid Polyak, to me, he really is a really good synthesis person for the Arctic Ocean. And he published a paper suggesting from cores across the Arctic Ocean that had been taken at the time, that up until the MPT, the Arctic Ocean had just seasonal ice. That's kind of shocking for a lot of people to think about. Wait a minute, the Greenland ice sheet's coming and going. We've got seasonal ice in the Arctic, you know, and there's a lot of other proxies, IP25, other records that, you know, would quibble with that. But using foraminifera and also Tom Cronin using his ostracods would agree that, in fact, you had mainly perennial ice after the MPT and seasonal ice before. So that's kind of interesting. What does that mean for our records? The other thing I want to point out to you about the MPT that had gotten my attention when these papers came out, because in this paper, let me explain. So the bottom is 0 to 1.5 million, and they're using a proxy that indicates overturning the creation of intermediate water in the North Pacific. So when the Bering Strait is closed, you get more production of North Pacific intermediate water. When the Bering Strait is open, you get less of that production. And what they do in this paper is, using this long record, is they try to make a case that, in fact, prior to the MPT, the Bering Strait was largely open. It didn't, so during glacial interglacial changes, the Bering Sea stayed open. So this means high sea level, or the sill depth changed, right? So it was open, and then after the MPT, we had glacial interglacial changes that allowed the Bering Strait to become a land bridge, and then submerged and back and forth. And so this got my attention. I read this paper and looked at this. You can see here's the minus 50-meter sill depth, and here's their estimate of the sea level with their proxies. And I thought to myself, wait a minute, that can't be true. I baffled over my mind. I thought, well, wait a minute, let's turn this around. What if that's true? And we need to then go back and study the Bering Strait and see whether that's in fact the case. So how do we get back at that? So I pulled out these really old slides from some work. This is David Hopkins, who was Mr. Landbridge for many years. He was my advisor. And he initially was famous for mapping shorelines in this part of Alaska. And what I want to point out to you is that we have, along this coastline in here, we have stage 11, and we also have these Pliocene shorelines, and they're tilted like this. So my elbow is the date line with Russia, and they're tilted like this over time. And so we'll go out, follow that arrow, and if you go out to the middle, there's two islands, the Big Diomede and Little Diomede. One's Russian, one's American, and they're both flat as a pancake. That top is a wave-cut platform, and we've been out there to do cosmogenic isotope dating on that. It's it's fraught with problems for Cosmo because of the intense weathering of the rocks out there. So we got really minimal ages. But nevertheless, the top of those islands match perfectly with some of our Pliocene shorelines. So this means, wait a minute, so this is coming up. It's rising 100 meters or more above sea level. The other thing, so this is one side of what we now know as a graben. Here's these tilted shorelines. The last interglacial goes back below sea level right in here. On this side in the mountains, small valley glaciers come out, and there are moraines. And I've actually seen this myself. The moraines are offset by faults of over 3 meters of offset. So even since the last glacial maximum, these faults are active. So this really got me thinking, what's going on here? And so it turns out that, and I thought this was fun, I just noticed this morning, this figure, that's Italy. So I thought, well, there must be a reason I'm using this figure. This is what they call Anatolian extrusion, that we have some modeling of what's happening in Alaska to this part of the Bering Sea. The Bering Sea is a plate, it's rotating, and in fact, so this graben structures, downfaulting and uplift, there's faulting that's going on here, let me get to that. There's also the subduction of the Pacific plate. So that plate is subducting, you're getting remelting, and of course a rise of magma, a rise from this subduction zone. And this is rotating clockwise. And in fact, if you go to Kamchatka, you can find the entire Pliocene and Pleistocene section in a riverbed because it's all tilted up on end because it's all been compressed. And you can just literally walk through the Pliocene and the Pleistocene in Kamchatka because of this rotation. So we've got tectonics going on, we've got GIA, the glacial impacts, and when did this all happen? We know that the Bering Strait itself opened around 5 million years ago. When did it close? When was it open? How long did it stay open? I don't think we know. I don't think we really have a good handle on that. So again, thanks to Jeff Bond, who's in the audience, for these beautiful figures. This is Beringia here. Was Beringia, how often was it like this? How much was sea level leaking through at different times? I think this binary view of flooding during interglacials, exposure during glacials, probably too simple. This eustatic model is just not going to work. We've got to think otherwise about that. And the reason is, think of it. I mean, we just heard about those little voles that migrated to Denmark. We have to think about when was the land bridge open and closed. And so this I like to think of it as a check valve here. The influence of the fresher Pacific water on the North Atlantic and this gateway this way is just as important as it is for understanding the migration of plants and animals, eventually humans, and the exchange of DNA across this time period here. So this gateway is so important, and I think that getting this right, finding out, is most of the early Pleistocene seasonally ice-free and high sea level, so the land bridge was never exposed? That's an interesting question, and I think it has implications for a lot of our community to get this right. So I'm really hoping we can do that in the future. So borrowing from Ken Miller's sea level curve that he published a couple of years ago, this sea level curve also is intriguing to me to point out that, if we look at, in fact, I think the next slide has it a little better. Here, if we look at this time period, we have the 100K world, we have ice sheets that have the changes in ice volume seem to be around 130 meters plus or minus or so. But if we come into this period, the ice sheets are smaller. The amplitude of sea level, if you believe Ken Miller, and I'm sure there's a few people out there that don't believe Ken Miller's curve, but nevertheless, this suggests the ice sheets were smaller. They came and went during the 41K world. They were more dynamic. They were capable of producing super interglacials with small forcings probably due to Milankovitch. The question is when was the Bering Sea open? This line, by the way, right through the middle of that figure is -50. That's the Bering Straits. So I think we really need to think about a lot less sea ice and how high was sea level in these earlier periods when it's so difficult to manage. And in the red stars here are the shorelines that I've mapped on the north coast of Alaska, just to give that some. So that's, again, only a partial record of real sea level. Okay, so let's think about those ice sheets, how dynamic they are. This was a really exciting paper that really pushed the community to think about Greenland, the Greenland ice sheet coming and going and coming and going. And so Schaefer et al. Suggested what I call the Goldilocks exposure histories here, where measuring the beryllium and aluminum in the bottom of the ice cores here at Summit. They measured that and then tried to figure out, is it all exposed and then ice covered, or were these little red tick marks different times when it was exposed, or what was the history like? And so, so here they are, just blown up a little bit. You can see this is, which one is the right one, which one makes the most sense across from 41K world to the MPT to the 100K world. So to test this, one of our graduate students, who's now a postdoc in Texas, Benjamin Kiesling, he presented this a couple years ago at AGU, so I'm borrowing it back from him now. He ran an ice sheet model to predict the beryllium as a function of exposure in the Greenland ice sheet, below the Greenland ice sheet. So he then extracted that exposure history and then compared it to observations. And what he was able to do, and he drove this model, by the way, using the paleo temperature record from Lake Elgagikkan. So he got 2 different scenarios that seem to make sense. He can't eliminate these 2, but the red bars are times when the Greenland ice sheet may have been gone, using the Elgagikkan model, climate model from the other side of the Arctic. So he hasn't published it yet. You guys know how it goes. The temperature record hasn't been published yet. So as soon as the temperature record's published, then Benjamin can publish this model. But I know he's been shopping it around. So it suggests that, wow, these ice sheets can come and go a lot more quickly than we thought. And I think we're all aware of that ourselves, and we have to communicate that to policymakers. They don't realize what could happen in the future. So how do we get at this? We need more records. We were hoping to go up to leg 377. Rudiger Stein and others, Karen St. John, had our chief scientists to be on leg 377, and I was supposed to be on that ship. And then Putin invaded Ukraine, and they canceled it. They didn't just delay it. They canceled it. And yet we were hoping to get an amazing record that would allow us to bring together the Arctic Ocean and the borderland story, climate history together. This would have been so exciting. And then leg 404, I was supposed to be on that one. They just canceled that one so they could demobilize the JOIDES resolution, which is so sad. But in a few weeks, leg 400 is going to happen. That's going to do work in Baffin Bay, so we're really excited what we can get from that. And of course, there's the last leg will be 403, just off the Svalbard margin. So hopefully we'll learn some more, but I really hope that somehow we can get back to this site that's been identified where we have the potential for a really long record to compare with the borderlands. Okay, so where are we headed now? So I've just made the point that we're here in this CO2 world, and I was in one of my meetings, again, meeting with people in the IPCC, the negotiators, a few weeks ago. There were several of us volunteer our time to talk to them about the science. I heard some scientists from the UK say, they explained that once we get above 450 ppm, that this may make a major pH change in the Southern Ocean and the Arctic Ocean. And we're only 11 years from that. So this is kind of frightening. There's a tipping point that we're approaching with ocean acidification. We know that the sea ice, we've already tipped it, and most people, the sea ice people, have agreed that it's gone. Even if we stopped all the CO2 in the world today or tomorrow, we're still going to lose the sea ice. The sea ice is going to start to disappear in September and eventually into August over time. So that tipping point, we kind of blew by that one. The next one might be ocean acidification. And then the next one might be the ice sheets. So a lot of you in the room are already modeling and thinking about the Greenland ice sheet, of course, and we now know that at least some models can get rid of it in less than 950 years, if with business as usual, with the consequences for sea level. And of course, Antarctica is also undergoing massive change. And we see that before our eyes, and again, thanks to the Thwaites Glacier project and many other projects that are going around the Antarctic ice sheet, we're beginning to learn much more about how quickly things are changing there. And this figure, I've actually seen it in a few talks here at the meeting already. The fear is that, in fact, this dotted line that was so controversial to get into the IPCC, more people are thinking, boy, maybe it is not so unlikely. And there's a paper coming out from Martin Siegert in a few weeks, again, making the point that we're leaning a little bit more toward this might actually be something in our future if we're not careful. So this paper I really liked, suggesting tipping points here for the Greenland ice sheet. It has a threshold of 1.5 degrees. It suggests the West Antarctic ice sheet has a threshold also of 1.5 degrees. Maybe the marine-based parts of West Antarctica have a threshold at 3 degrees. These are the kinds of things we need to think about and quantify, and to see, how quickly are we going to go past these tipping points of perhaps no return. So just kind of wrap up here. I know a lot of you do a lot of outreach. We need to keep doing that outreach. Every opportunity you have to talk to the public, to talk to policymakers, please do so. Share with them what you know. We've got here, this is a reconstruction from Sedai that showed, because of the way sea level operates, some of these low-lying Pacific islands here are going to be more largely affected by sea level because of their position relative to the polar regions. And yet they're not the ones that have caused this problem, of course. And so I could, okay, it's stopped going forward. Could you go to the next slide, please? The technician in the back. Oh, he came out from behind the curtain. There he is. Okay, could you go to the next slide, please? My hunch is I've just lost the batteries in this thing. Can you go then? Okay. So the next couple of slides, I just want to very quickly show you a website where you can actually play with sea level and pick out your favorite place. Again, I'm talking with policymakers. If you're in Sweden, you talk about the coastline of Sweden. If you're in the UK, you talk about the coastlines in the UK. Show people their backyards, what's going to happen to their area. And so here, this website, Climate Central, gives you land projections for what's going to flood by 2050. You can pick out your favorite place. This is Belize at 1 meter. Let's see if this works. Next slide, please. This is whoop, next slide. Okay, that's 3 meters for Belize. Next slide. Next slide. Pardon? Okay, now it's working. So here's the Marshall Islands at 0.4 meters, and if you zoom into the island on the west side there's 0.4 meters, 2 meters. So this is real for these people. But I also want to say something about what I'm doing is working with some indigenous people in the Yukon-Kuskokwim Delta through the Navigating the New Arctic program through the National Science Foundation, there are at least 30 villages where flooding, sea level rise, and the thawing of the permafrost are completely undoing their infrastructure. And so we're working with them to do the planning together, to co-produce a future and give them the tools to think about their future. This really is, I like to call it Alaska's Bangladesh. It really is flat and it's submerging. And so we're doing our best with working with civil engineers and quaternary geologists to help think about this part. So again, let me wrap up here, the last slide. Just some remembering forward. The transition from a forested Arctic to one of tundra is complicated. The Arctic evidence supports that the mid-Pleistocene transition in Beringia may have been a little more interesting than we thought. We don't really understand the long-term history of the Bering Strait, so we've got to work on that together with tectonics and GIA, dynamic topography, and the geologic record. Numerous superinterglacials demonstrate the ice sheets were not stable features, and the Paris Agreement at 1.5 is probably still too warm, just like this room. And we need to really have and insist on a no regrets policies for managing the planet, no regrets. Some of us feel like we're already getting some regrets, but we really need a no regrets future. And with that, thank you very much for your attention.
Yes, an apology for the technical problems.
Okay, it's all right. Oh.
Give you a replication of the original game of the Congress that was held in Rome in 1950.
Oh, thank you.
So 70 years old.
Okay, I would like to thank you very much for attending this plenary speaker. I would like to thank the speaker again. It shows why it was a good choice to invite her, and we are very, very happy with your contribution. Thank you again.